So, yesterday we started talking about the idea of these collisions transferring momentum from one object to another. Uh, and this happens through an impulse. I believe we talked about force time. Yeah, right here is our impulse, right? We talked about the definition of an impulse. An impulse is a force that acts on an object over an amount of time. An impulse is, they use J for impulse in this book. Some books use I for impulse, but this is the engineering version. So the J is the vector that takes the force that's applied times the time that it takes to apply it. And that's where we have an impulse. An impulse is also equal to the change in momentum of the object. So whatever object is having that force applied to it is going to have some change in momentum because of that force. It's going to change its movement somehow. And that change in momentum is equal to that impulse. And we talked about the crater idea. So in the idea of here's a really good example though. As the meteor hits the Earth, this big old, huge thing hits the Earth, where is the evidence that momentum has been transferred from the meteor to something else? Okay, why is the crater evidence that it has transferred momentum? What's that? It's moved the dirt, right? It's moved the earth. It's moved rocks and dirt and dust and whatever else was there. Maybe plants, maybe animals, who knows what was there. And whatever was there got moved, right? In fact, some of it got moved so fast that it just disintegrated into little bits of stuff, right? And all of that movement, if you added up all the momentum of all the moving dirt, dust, rocks, animals, plants, whatever it was that was moving, and added up all those changes in momentum that occurred, and then included one more thing, there's one more thing that changed its momentum. And that's the Earth itself. A meteor of that size will actually change the momentum of the Earth slightly. Not much, but slightly. Some meteor strikes are big enough to completely change the movement of a planet, knock it off its orbit, those kinds of things. But this one certainly would have some small impact on that. But it certainly changed the Earth's momentum as well. And if you added all those changes in momentums, including the change in momentum of the meteor, because the meteor, even if it sticks to the Earth, doesn't necessarily end up not moving because the Earth is moving, right? So it essentially has the same momentum of the Earth eventually. But if you added up all those momentums, you would actually find that the change in all those momentums from where they were to where they are now after the impact would equal that force times that change in time. And if you added all the momentums before the thing happened, the meteor plus the Earth, and anything on the Earth, added all those momentums and then added all the momentums of the things afterwards, those two things would be equal. Because momentum is truly conserved. You have to be very careful the way that you do that. In particular, the best way to do it is to calculate a slightly different type of momentum, what you call the angular momentum. But we'll get to that soon. So, then we talked about this force time graph. Remember, we had something similar to this in the previous chapter where we had the force distance graph, where the area under the force distance graph was the energy. In this case, or rather the work we called it, which is just a form of energy. And in this case, the area under the curve is now the impulse, or the change in momentum. And then we talked about the benefits of this impulse having time in it, because we can take advantage of that by extending the time that a that an impact takes place, or extending the time of a collision, so that that force that is applied can be smaller over a longer time and still have the same change in momentum. So when you're bringing a car from going 27 meters per second to a standstill at 0 meters per second relative to the Earth, all of that change in momentum is going to require a force times the time. And if we take longer in that time, if the time is bigger, the force can be smaller and still have the same change in momentum or the same impulse. So we allow the car to crush, we allow it to crumple, we deploy an airbag so that as the person's head comes forward, they don't have this sudden change of momentum as they go from moving to stop, as they hit the windshield or the steering wheel. So we stretch things out in time as much as we possibly can so that we do not break the human driving the car. They actually ask us to calculate this. They tell us that it happens in about 2.5 seconds, and it's 860 Newton person, and they have a 27 meter per second initial velocity. So if we know the initial velocity, we know the time, then we can calculate the acceleration going from 27 to 0 in 2.5 meters or 2.5 seconds, right? So that's what they do. They calculate that acceleration, and then they multiply the weight of the driver times that acceleration to get the force required to slow down that driver. And so here they do that. 860 newtons. Well, here they actually calculate the weight of the person. But here they're calculating they're using here is the weight of the person. They're calculating the mass of the person. You need the mass, and they gave us the weight. So then they put the mass into this equation where we have a kinematic equation here, the change in velocity over time, and then mass times change in velocity over time is mass times acceleration, right? And the mass, of course, is the 87. They put in the 27 for the change in velocity, and we get 940 newtons in the I-hat direction. It's a negative because it is going to go in the opposite direction from the positive direction. We're saying that to the right is positive here. So this is negative because it's backwards to stop. So what happens if this happens in 0.2 of a second, which is what happens when your head just hits the steering wheel. That's much more like 0.2 of a second. In fact, it's probably even faster than that. It's so fast you won't even really experience it happening. It's probably closer to about 1/10 of a second. But anyway, 0.2 of a second you can perceive. 1/10 of a second, very difficult to perceive. And this same acceleration in that same amount of time with the same mass, and this much shorter time with the same mass, gives you 11,853 newtons. Notice that the weight of the person is 860 newtons, and so when they hit the airbag, it's just like falling on their own weight, with their own weight essentially. It's the same amount of force that they feel on their feet. It'd be like somebody standing on their head for a second. Here, this is 10 times that. No. Yes. 14 times, says right there. Good. So anyway, bad news. That's just a lot of force. Not very likely you're going to survive that. Especially since this is 27 meters per second, which is about 60 miles an hour. That's cooking. That's moving. Hit a steering wheel in 0.2 of a second at that speed. It's going to do some serious damage. And this is actually why seatbelts are designed the way that they are designed as well. It used to be like I had a 1967 Volkswagen and a 1966 Volkswagen growing up when I was learning to drive. And in the 66 Volkswagen, it just had a belt that was bolted to the floor. In fact, the belt didn't even come with the car. When the car was built, it had no seat belts. And then my dad added the seat belt in later. And it was just bolted to the floor, and it was just two straps with a belt on it. And you just lift them up, and you kind of tighten it. And that was it. And that was the whole thing. So there was The seatbelts we have now, of course, have this retractable thing, and that's not just for convenience so that it will get out of your way when you're in the car. It actually is designed to not engage immediately. It's designed to give you a little bit of slowing down and then stop you. And that's, again, to increase that time of the change in momentum, the impulse. So, gotta have Star Trek. Okay. I don't know why they're using this as an example, but that's okay. In this one, they're talking about they're just talking about if you give let's see, what are they're saying that here they're using Star Trek as an example because in Star Trek they use impulse as a amount of speed. So for impulse, you have one fourth impulse, for example, is 1/4 the speed of light, and then they want us to calculate how much impulse it actually was applied to the ship. If the ship has a particular mass, so the mass is 2 times 10 to the 9 or 2 billion kilograms, and if that's the mass and this is the velocity, multiply them together, mass times change in velocity rather, because it is the change in velocity, and that will give you your impulse or your change in momentum, and then the impulse is also equal to force times change in time. So you have to set the mass times change in velocity equal to the force times the change in time to get this equation. And then you solve for the force, which in this case would be 2.5 times 10 to the 15 newtons. So it's a huge amount of force. Here they say, that would be such a force would kill everyone on board instantly. And it's true, especially considering that whenever you watch one of these Star Trek movies, that speed happens just in a few seconds, a change in speed. But they actually take care of that in they have a thing called inertial dampers, and we don't have any idea how they would work actually. But they did take it into account. That's the great thing about Star Trek, is they do think about the physics. They think, well, these kinds of speeds, the kinds of speeds that it would take to travel from one star to another star are way beyond our ability to achieve for many reasons. Not only is there an inexhaustible amounts of fuel that you would need, it's just you would need so much fuel. You would have to have a fuel source that could not run out ever. I mean, that's really what you would need. And it would have to be fit in a small space. That's one huge problem. The other problem is these ships that they build in Star Trek are so much bigger than spaceships are today. The biggest spaceship we've ever built so far today is the Space Shuttle, and it is a tiny thing. Like, the entire workspace of the Space Shuttle is smaller than this room. Much smaller. You would be surprised how small it is. But if you look at the Space Shuttle, the only place that the people actually work in is the very front part where the windows are. The entire back space is all just cargo area and other things like fuel storage. But where the astronauts actually work is just in that very, very small front space, which is probably about a third, probably about a sixth the size of this room. Just break this into 6 pieces, and this little section up here is probably all that you have to live in for a week or two or however long you're up there. And that's the biggest one we ever built. We have a space station, but it's not really a spaceship. Anyway. So they invent these inertial dampeners, which essentially remove the the experience from the inside of the ship so that you don't feel these accelerations. Who knows how they work? Anyway, if they stopped working, everybody would die. U.S. Air Force uses 10 Gs, which is 10 times gravity, 10 times 9.8, as the maximum acceleration a human can withstand, but only for several seconds, and survive. Right? How much time must the Enterprise spend accelerating if humans on board are to experience an average of 10 Gs of acceleration? If you do this math, if you're going to actually go to, if you're going to have the same acceleration that you would have from 10 Gs of acceleration, and try to get up to this speed, it would take. I'm guessing, but I'm not going to do the calculation right now. But I'm guessing it's going to be somewhere in the years range, years to get up to speed, and years to slow back down again. Right? It's a lot of change in momentum. The speed of light is very, very, very high. It's a big number. And getting to a quarter of the speed of light is, we don't have enough fuel on the planet to do that. We just don't. Unless we consider a new form of fuel, which Star Trek also figured out. They also determined that an antimatter reaction, a matter-antimatter reaction that goes through some specific crystal that doesn't exist in nature really, is going to provide this huge amount of energy. And maybe someday it will. Anyway. Let's see. Here they talk about dropping the phone and seeing, and you're essentially calculating that change in impulse again. This one is interesting because they don't actually tell us. I'm looking to see if they tell us, but I don't think that they do. They don't actually tell us the time that the collision, that how long the collision takes. And so when they don't tell you the time that the collision takes, so they don't say that it takes a tenth of a second or something like that, and you're dropping it from some distance or you're coming in from some distance and then colliding with something, then what you have to do is you have to figure out the average change, the average force that it feels during that entire time. So if it's coming in from a meter away and then it goes back out to a meter away, you kind of have to consider that entire time as the time of the collision, because you don't exactly know where, when it actually collides with the wall and how long that collision takes. All you know is that it went from one point and then it came back to that point. So somewhere in between that point, it being at that point at the same time, or that same point twice rather, it collided with something. That's all you really know technically. And this is a strategy that we'll use later on to develop. Well, this is a strategy that is used in physics, in thermodynamics, to develop what's called what is it called? It's called this. I can't remember what it's called now. It's some theory, but it's a theory that is used in chemistry quite a lot, and it's used in physics quite a lot. But essentially, it's this theory that, oh man, what is the name of it? I can't remember. But it's the theory that heat is actually just movement of particles. The kinetic theory of gases. That's what it's called. It's called the kinetic theory of gases. And it's the theory that when you add heat to a system, heat energy to a system, all that really does to the system is it speeds up the particles in the system. And as they go faster and faster and faster, you get a higher temperature. And all temperature is just movement of particles, right? So when you see the thermometer go up in one of these little alcohol thermometers, all you're really seeing is the molecules in the alcohol are just moving faster, so they start to spread out from each other more, so they move up the thermometer a little bit, which is extremely useful because we have a tendency to believe that that temperature is something very different, that heat is something very different than other kinds of energy, but it is not. Heat and temperature and all that is no different than kinetic energy. It is exactly what it is. It is kinetic energy. We observe it differently because it's something happening on a microcosmic scale that we have a difficult time measuring on a macrocosmic scale. So we use these things in contact with those molecules, and we watch them change as they expand or whatever, and we call it temperature. We call it temperature. It's not really anything different. And that's quite important because when people started to try to study temperature, they didn't know that, first of all, and they were making assumptions that were completely incorrect because they didn't know that. And once they they made one discovery. It was Lord Kelvin that made the discovery that absolute zero is a place. There is a place where you can get cold and no colder, right? That discovery was made about the same time as we started figuring out that heat was the movement of particles, and we were able to explain absolute zero using that. That discovery of Lord Kelvin was unexplainable until we figured out that when the particles stop, you're at absolute zero. That's actually when the velocity of the particles is zero. And also, we've been able to achieve the coldest temperatures by understanding that. We don't achieve cold temperatures by doing cryogenic cooling or any kind of cooling as far as putting you in contact with something cold, because there is nothing cold enough to get close to absolute zero. The way that we've achieved things close to absolute zero, which is, I think the closest we've come is 10 to the minus 11 at this point, so about 10 to the minus 11. The way that we've achieved that, though, is not through cryogenics of any kind, not through any kind of chemical reaction of any kind that removes heat, quote unquote, from a system. We've done it by manipulating the actual atoms. We've done it by using lasers to actually slow down the atoms to the point that they're almost standing still. So that's just interesting application of this knowledge, I think. That happened just recently. That's happened just in the past few decades. Anyway, so dropping the phone, the change in momentum thing. Here they actually are going to also calculate the energies going on. We have kinetic energy and potential energies, right? As you drop the phone. And they end up calculating the force in the same way. It ends up being you have the change in momentum. There we go. Sorry, my brain's turning off. Force, so change in momentum or impulse equals force times time. So force equals change in momentum over time. And they use some kinematics to calculate up here, for example. And they also use to calculate acceleration and so on and so forth. Same kind of idea. And of course, you can rearrange the equation to calculate the force, which is what we've done a couple of times already. It's nothing new. And you can do it using calculus as well, because if your change in momentum here is has a constant velocity, if your change in momentum has a velocity that is changing uniformly, you could say, I guess, as a linear change, then this becomes quite easy to estimate. But this just the average essentially becomes the actual force. But if your momentum is actually time dependent, if the momentum changes in time on its own also, then you actually have to do an integral, or well, you have to define it as a derivative, and then to solve for it, you have to solve it as an integral. And they do this tennis ball on the tennis racket example again. Let's see, do they actually give us a function for that? They don't. But in this one, they're, again, just using, they have a final speed and a mass. The initial speed of the ball, of course, is 0. So your change in speed is 58 meters per second. They tell us the time that remains in contact. So this is actually not, they're not going to use calculus at all here. They show it in calculus at the beginning, but then they immediately turn it into just deltas instead of derivatives, because they're assuming that that force is, they're assuming that the force applied to the tennis ball is constant, essentially. So that change in velocity is very linear, and it just obeys this algebraic rule, which is fine. And they plug in the numbers, and they get a force of 6.6 times 10 to the 2 newtons, which is technically this is the average force, because we don't necessarily know that force is constant, but this would be the average force. Okay, so now we've talked about impulse, momentum, and how impulse and momentum are related. Impulse is change in momentum. Then we can start to talk about the conservation of linear momentum. And we talk about linear momentum again because linear momentum is the simplest form of momentum. In reality, linear momentum is a difficult thing to talk about since nothing in the universe is really linear. Everything's always rotating and going curves and all these things. But momentum is conserved, especially when you look at, so linear momentum can be conserved in very simple situations, very simple systems, but in general, momentum is conserved as well, always. So what does this mean? This means that when you measure the momentum of a system at any given point in time, and you measure the momentum in a system at any other given point in time, as long as this system is closed. What does it mean to be closed? It means there are no forces that are acting from the system on the outside world and causing a transfer of momentum out of the system. And there are no forces from the outside world acting on the system causing a transfer of momentum into the system. It means that the momentums can transfer back and forth within the system, but not outside the system. So if your system is two cars, colliding with each other, then the transfer of momentum is as long as those cars don't interact with the outside world, the transfer of momentum will be conserved. Now, what does that mean, the outside world? Well, normally when two cars collide, one of them hits their brakes, at least you'd hope. But they don't always. But even if they don't hit their brakes, the cars will push against each other, and one of them will slide backwards maybe, and their wheels will scrape against each other. Whenever you have a force acting on the ground, that's going to be a force on the outside world, which is going to change the momentum of the outside world. In particular, that would change the momentum of the Earth. As you crash and you skid against the ground receives a bit of that momentum. A little change in momentum of the Earth. Not much, because the Earth is so massive compared to the cars that it's not going to absorb a whole lot of momentum there. We're not going to be making the Earth move very much, in other words. It just doesn't, the Earth has so much of its own mass, its own inertia, that it's just not going to change it much. And, you add that to all the cars crashing on the other side of the Earth and you're fine. But so what we try to do is we try to create these situations where we don't have to worry about momentum transferring out of the system because of forces on the system. So we try to get rid of things like friction. Friction will transfer momentum out of the system so that you will notice that loss. The Earth, you won't be able to see it in the Earth's rotation because the Earth won't notice it much. but you will see the loss of momentum as the cars crash. We see this all the time. When cars crash, they come to a stop usually, even after a short distance. Even if one of them is a big semi, they eventually come to a stop. And the reason is because they've transferred all the momentum into the earth or into the air, things that are moving around them. But we don't see that. We don't see how the Earth's momentum has changed. It's too small of an effect. But it's a big effect on the cars, right? Anyway, point being is that it is conserved, but not only is the actual value of the momentum conserved, but the direction of the momentum is conserved. So if the overall momentum of the system is 0, and because it's 0, it has no direction, and then later on, you see one part of the system flying off in some direction. Let's say it's flying off to the northwest. Then the other part of the system is probably going to be flying where? If one of it's moving off to the northwest, which would be this one, the other one would probably be going somewhere off to the southeast, right? Now the details are in the math, but that's kind of the idea, and this happens all the time. For example, with rockets, you fire a rocket up in the air, and then there's a second stage where the top of the rocket blasts off of the bottom of the rocket. What happens to the bottom of the rocket if the top one goes up? It goes down, right? And it comes back to Earth often. That's actually a good thing. They can retrieve the rocket and use it again. And it's also a good thing for the rocket going off into space, because it's if the stage on top is much smaller and much less massive, and it pushes on this bottom one that's much more massive, the bottom one won't move much backward, but the top one will move a lot forward because of conservation of momentum. The mass, and it looks like this if we look at it. Let's take a look at some of these examples in writing. Where's my thing? Here it is. So let's talk about the rocket one is a great example. You have this big stage here, and this one's quite massive. It has a big M, and they're going the same velocity to begin with. They have this same V, and then you have this smaller M, but it has the same velocity V because they're moving together upward, right? So the overall momentum of this is little m plus big M, total mass times the V, or this one plus this one, right? Then the top one has a little rocket booster on it, and it shoots off the rocket booster, and it goes off in this direction, right? It gets some thrust in this direction, some force or some change in momentum, some force, an impulse, right? A force times change in time, or which is equal to a change in momentum, which is equal to an impulse. And the direction of that impulse is up. And it's pretty big, right? And it's pretty big because the force times change in time is also equal to a change in momentum. A change in momentum is equal to a mass times change in velocity, right? It's a little mass, and because it's a little mass, the change in velocity is actually quite big for this impulse. For the rocket, for the base of the rocket, it also gets a push, but its push is actually this way, right? It ends up with the same momentum. It gets the same thing here, the same momentum. It equals the same impulse, but because it has such a bigger mass, then its change in velocity is different. It's a much smaller change in velocity, right? And let's see what else do I want to say here. Oh, yeah. The other thing is this one is, let's say this way is the positive direction. This one would be positive, and this one would be negative. Right? So it's equal in magnitude, but opposite in direction. This way, the overall momentum is still conserved. This one changes its velocity a little bit, but it changes its momentum the same as this one. This one changes its velocity a lot, but its momentum changes this one. So the overall momentum is still the same. it still has this overall momentum that it started with, even though this one might be going backwards. If this one's going backwards, then this one must be going forwards a lot faster to make up for it. And the overall momentum stays the same. So, this doesn't work with kinetic energy, by the way. Kinetic energy is not conserved in this situation at all. You can try it out, it just doesn't come out, it doesn't work out. And but momentum does. So momentum does stay conserved mathematically and in real life. Another example of this would be well, the classic one, which we're going to see pretty soon, I think, would be the billiard balls, right? So you have the billiard ball, you have the cue ball coming in and hits another ball, hits it off center a little bit, so that the cue ball ends up going up this way, and this ball goes where? Down this way, kind of, right? Why? Well, because the momentum is going this direction to begin with. That's the overall momentum. This one has a momentum of 0 to start with, and all the momentum is in this ball. And if the momentum is represented by this length of this arrow, then the overall momentum at the end, the total momentum at the end, has to be also represented by this arrow. Same length, same direction. Well, how is that possible? Well, this ball up here might have a momentum of about this much this direction, if we do the kind of vector thing. Then this one would have a momentum about this much in this direction. And what happens when we add those two momentums together? What's that? Yeah, the y directions cancel, right? Because this one and this one are opposite, and they will actually end up having equal momentums. And it doesn't even matter if they're the same size ball, the same mass ball. This will happen no matter what. But they still have some momentum in this direction. This one would have a little bit, and this one would have a little bit. And if you added them together, they would equal this one. So this one would end up being actually longer than it looks, but or we change the length of these or whatever. But the momentums will add up to equal that final momentum again, even though we've got this split in these different directions going on. So this is kind of the classic example here of momentum, the billiard balls. Okay, let's go to here. So conservation of momentum, right? This actually is something that you can put together from the idea of so they're putting this together from the idea of Newton's third law. Yeah, the Newton's third law says that you have a force acting on an object, and there's always an equal and opposite force acting back on the original object from the object it's pushing, right? So force on 2 from 1 is equal to negative force on 1 from 2. And the force on 2 from 1 is equal to mass of 1 times the acceleration of 1. And likewise for the force of 1 on 2. So you get this equation here. Right? Well, acceleration is the first derivative of the velocity in time. So you get this equation. But it turns out that these things are not equal. The change in velocity of the one and the change in velocity of the other are not equal. Even though these two things are equal, these two things are not equal. In other words, acceleration 1 and acceleration 2 are not equal. We knew this, right? This is the whole two people pushing on each other on the ice or something. Which one moves faster after they push against each other? Which person moves faster? Which one accelerates more? The smaller person, right? Whoever is smaller in mass, will accelerate more because smaller number here means you can have a bigger number here and still be equal to this thing over here that has a bigger number and a smaller number, right? So we know these two things are not equal, right? However, if you put in the masses, they are equal still. So this is still equal. And they go ahead and do this little trick where they put the mass inside the derivative because it's constant, which is totally fine. Go ahead and do that. This is not absolutely true in every situation in physics. Sometimes masses do change, like with the rocket that's firing off its rockets, it loses mass as it fires its rockets. But we're just going to assume that we can do all this stuff. But anyway, and this just shows us that the change in momentum in time on each side is equal, right? And then you have the change in momentum plus change in momentum equals 0 if you essentially just put this one on this side, right? I'm just solving these things. And then by one of the rules of calculus, you can actually add the two momentums together and then take their derivative in time. And this actually implies that P1 plus P2 is a constant. Because if you take the time derivative of anything and it equals 0, it's a constant, right? So this is actually your first foray into differential equations. Right? When you have an equation with differentials in it and you solve it for the solution for this one is that the momentums are, the sum of the momentum is a constant. That is the solution. That means that the momentums, when they're added together, cannot be time dependent as a group, essentially. This, whenever you get to this point where you have something that happened, some measurement of a system before and some measurement of a system after, added together equaling a constant, that tells you that you have conservation. So that's the conservation requirement right there. And here they do the billiard ball one again. Here we have total, let's see, what are they doing? P1, P2. So before so this one's coming this way, this one's going this way, and they're going to hit each other, right? So the total momentum before is P1 plus P2. So it's down like this, right? If you add two vectors, you put them head to tail, and then you go from the tail of the first to the head of the second, and that's the sum of the vectors. Well, this is a picture of them afterwards. Now this one is going this way, and this one's going down. Well, this one and down is still the same total momentum. So this could easily be the result of this. Right? Are there other results that could happen? Yeah, there are some other results. Every result that ends up giving you this vector as your final vector for the sum of momentums is going to be a possible result of hitting those two balls together. Right? What it depends on is really what part of the balls hit together. So if they hit head on, of course, one ball is just going to stop. Well, if they hit head on, you're going to have a very different result than if they hit off slightly. One ball kind of grazes the other one, right? That's where the difference will be in each collision. So what is the general equation? You add all your momentums together for any number of objects you want, and it has to equal constant, so you have a summation. It's pretty simple. And we have this notation here where we talk about, this is, can't remember what they call this notation, but anyway, this essentially just means the total change in momentum of the system. Sorry. No, this is not. This is the mass. This is the mass of the system. Sorry. This is the total mass change of the system. So if your system, when you're dealing with momentum, often has multiple separate masses. And if one of them loses a little bit of mass, then the other one must gain that mass in some way, and that has to be part of your system if you want to use conservation momentum. So we go back to the idea of the rocket. The rocket, when it burns fuel, it exhausts that fuel out the back. You have to take that fuel into account as part of your system. So you have to measure the velocity of that fuel, and you have to know how much mass is in that fuel as it leaves the rocket in order for you to conserve momentum. Because the momentum of the fuel coming out the back of the ship is going to equal the new momentum or the change in momentum of the ship moving forward, right? So that's kind of important. And then your net external force on the system must be zero. So that means no forces in and out of the system causing changes in transfers of momentum. And that's where we're going to stop for today. We're going to talk about some specific systems and give you some examples that you can try out next time on Wednesday. I'm going to do a bunch of examples of these and set you loose on them. How many homework questions do I have in this homework? I can't remember. What's that? 2? Well, I need to put some homework in. Oh, that's right, because those 2 came from chapter 8, and I haven't finished up chapter. So I'm going to put some homework problems in the homework right now, and then you guys can get started on them. A lot of them will be very simple stuff like we've done so far to start off with, like calculate the impulse from this change in momentum of the system. But then they'll get into more of the conservation momentum stuff later.
Also, you still haven't added the point for chapter 7.
I will get to it, I promise. All right.